What's up guys? In this video we will be covering the 2023 FRQ from the AP Physics 1 test. So first we have a simple energy conservation problem, number 1. So let's read the problem. Cart on a horizontal surface attached to a spring as pictured above. One end is attached to a wall, the other is held at rest. When the cart is released, the system oscillates between plus L and minus L as shown above. And then we have a graph of kinetic and potential energy with kinetic on the y-axis and potential on the x-axis. So number 1, A asks, on the graph of the kinetic energy K versus U, the values of x and y intercept are the same, and they're asking why using physics principles. So as you know, by conservation of energy, which we have learned, the total energy in a system, mechanical energy, has to equal potential plus kinetic as long as there are no outside forces, non-conservative forces acting on the system. And since we know that there is no friction, there are no outside forces on the system, so we know that energy will be conserved. So first let's look at plus L. Before we release the cart, all of the energy is going to be potential because the cart is not moving, so there cannot be kinetic. But then when we're at the equilibrium point, the cart will be moving at full speed, but there will be no potential energy, so it will be all kinetic energy. Those represent the 2 points. The point where there's no potential and all kinetic, and the point where it's all potential and no kinetic. And these 2 points will obviously have the same values because mechanical energy has to equal the same. So 4 plus 0 or 0 plus 4 both equal 4, which is why they're the same value. Alright, so now we're at number 1b. So for this one, it's the same problem as last time, but we have a new block of mass 3mo dropped onto the system. So when we drop the new mass onto the system, the frequency is going to change because now a bigger mass is being oscillated, which means that it's going to go slower, in theory. We're trying to calculate the numerical ratio, which is possible because we're given both masses. In order to do this, we can use the formula that we're given on the formula sheet. So here we're given period equals 2 pi square root of m over k. This is for simple harmonic motion. You can use it for all simple harmonic motion problems. So this is period. We want frequency, which is just 1 over period. So if we invert this equation, we get 1 over 2 pi square root of k over m. And then we use the ratio f2 over f1. So we already have the masses that are going to be on the system. So f2, remember f2 is not 3m, but it's actually 4m because you're adding the mass on top of the already existing mass m, so it's going to be 1 over 2 pi square root of k over 4m, and on the bottom you have 1 over 2 pi square root of k over m. So first we cancel what we can and cancel m, so we're left with equal to square root of 1 over 4 over 1, and the square root of 1/4 is just 1/2, so that is our answer. Alright, now on to 1c. The dashed line in figure 4 shows kinetic energy K versus U of the system after the new block is dropped onto the cart. So this is identical to the one we saw in part A. So why must both graphs be the same using physics principles? So in order to answer this, we're going to take a similar approach to the first one. So first, we know that no work was done on the system because even though we dropped the extra mass on, no external force was actually applied to the system. And also, the potential energy in the spring was constant. No matter what mass you put at the back of the spring, the kinetic potential energy of the spring will stay the same. And we know that spring energy, the formula is also given to us on the formula sheet. It's equal to 1 over 2 kx squared. You'll notice there's no mass in this formula. It's because spring energy isn't dependent on mass, which means that even if we added the extra mass, it won't affect the total energy in the system, which is why the graph must stay the same. So there are several answers to this question that would have been taken. Now for C2. After the block is dropped onto the cart, consider a system of only the cart and the spring. On figure 4, sketch a solid line that shows the kinetic energy of the system that's only the cart and the spring, but not the block after the block is dropped. So if we go back to the picture on the last one, right here, so they're asking for the energy of just this and the spring. So in order to do that, what do we have to do? So we know that the total energy in the system is the same, but before all of the energy was in the cart and the spring. But now 3/4 of the energy will go to 3/4 of the kinetic energy will have to go to the mass of block 3m because it's also part of the system, which means that when we draw a point here, we're going to have to put it here for our new line. And then what is the maximum potential energy we can have? Once again, potential energy of a spring is still 1/2 kx squared, which means that it can still have max potential energy. It will just sit here. So this will still be the same. It's just this is different because of the 3mo factor compared to just mo here. Alright, next we have the experimental design question. So when I took the test last year, I almost actually messed up this question. It was kind of tricky, but not really. It should be simple now, so I'll explain it. Students conduct an experiment to determine the acceleration a of a cart. The cart is released from rest at the top of a ramp at time t0 and moves down the ramp. And the x-axis we're defining parallel to the ramp, and its origin is at the top. And then we're collecting data in this table. So first, we want to find quantities that could be graphed to yield a straight line whose slope can be used to determine the acceleration a of the cart. So we can determine many quantities, but the safest bet here, I would say, is position and time squared. Now, why do we use this? Because if we remember our formula, kinematics, 1D kinematics, we had delta x equals v0t plus 1/2 at squared. Now, since we're starting from rest, there's no v0t, so delta x would equal 1/2 at squared. So if we were to plot delta x versus time squared, it would be a linear straight line, and the slope would be this, which is easier to calculate, as it's just straight up giving us a as long as we multiply it by 2, because the slope will be 1/2 a, not a. So let's put that into the graph here. So we put time squared, and then you get a TI during the test, so just go down your calculator, or you can put it into data and statistics if you want. Even if you don't have a TI, just square all the values and you'll get this. 599214. Okay, so now that we have this, we go to the next part. Okay, so on the following grid, plot the appropriate quantities to create a graph that can be used to determine the acceleration a of the cart as it rolls down the ramp. Okay, so since I don't have the exact numbers that I drew on last time, I'll do a rough estimate. It should be pretty close though. So draw a slope here, slope here. This is our graph. Close enough. Okay, actually I messed that up, but okay, so we're gonna have time squared on the x-axis, time squared with units second squared, and then we have delta x here with units meters. So for our first, we're gonna go 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4. Okay, so when we're graphing this, okay, actually let's add the y-axis first. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Okay. Now we graph. So first point we had around 0.15, and 0.15 seconds at around 0.6 meters. So we'll go here. Second point we had like almost, I think, in the middle of the second section here. Third point was at 0.6 seconds and around between 0.2 and 0.3 meters, probably right there. Other point was between 0.8 and 0.1 seconds, leaning towards 0.1 seconds and more towards 0.4 meters. So it's right about here. And our last point was almost at 1.4 seconds, slightly above that, and the data point was in between 0.5 and 0.6 for displacement, so should be right about there. So if we were to draw a line here, it would go something like this. And then if you want the slope of this line, it will be, so we would be doing epsilon line. Okay, we would be doing delta x over t squared as the slope, and we remember that delta x equals 1 over 2 a t squared. So delta x over t squared would equal 1/2 a. So since this is m, so you put this multiple ways you can do this. You can just use like linear approximation, find two data points and just do your slope that way. Or if you did this all in a TI, you go to data and statistics, you press linear regression and you get your line, and whatever slope you get, you multiply that by 2 and it will give you your acceleration. So that is how you would do it if you use position and time squared. So what other ones could you have used? You could have done a velocity time graph. You could have done 2x and t squared, so that way your slope would have just been a, but it's not really that much simpler than just multiplying your slope at the end by 2. And a lot of people, especially teachers, prefer if you leave your coefficients in the slope and not on the axes, but ultimately up to you. You could do average velocity and then average velocity squared using the timeless equation that we also learned in kinematics. You could have done square root of x and time, which is the same thing, except you just square root both parts of our axes here, but you would still get the same idea. Alright, so now for part 4 of this problem. So it's clear. Okay, so question 2b. The students are asked to determine an experimental value for acceleration due to gravity, gxp, using their data. So what can they do here? First, what additional quantities the student needs to measure in order to calculate gxp from A. So first, we need to remember a couple of things to answer this question. So our acceleration was, we had a ramp, was down the ramp. Remember, acceleration goes down the ramp, but gravity will always point down. So in order to go from acceleration to gravity, we're going to need this angle theta right here. So we need theta, so we'll put that here, because we're going to need the sine opposite over hypotenuse to convert from acceleration to gravity. So we need theta. Alternatively, you could say you want the height of the ramp and the length of the ramp, because height over length would equal sine theta, because that is opposite over hypotenuse. Either one works. AP accepts both, so height and length or theta. Okay, and then the second part, write an expression for the value gexp in terms of A. So for this one, we can use our net force formula. We know that net force equals mass times acceleration. This we know. We also know that on the system, there's only really one force acting on it in this direction, because that's the direction the object is moving, so that's what we'll be equating it to, and this will equal the force of gravity, but only in this direction, the direction along the plane. So normally force of gravity will point down, that's mg, but once if we're going down the ramp, this is where it would point normally, but now we're going at an angle, so we're going to call it mg sine theta. However, since we're solving for gxp, this is actually gexp because it's based on the experimental value of A right here. So here you will note that m and m cancel, and we're left with A equals g sine theta, or alternatively, clear some space here, gexp equals A over sine theta, and that's how you would convert. Okay, now on to part C. The students calculate the value of gexp to be significantly lower than the accepted value. So now we're doing error analysis. What is a physical reason other than friction or air resistance that could lead to a significant difference in the experimentally determined value of gexp? So there's many factors that could influence this. So we have materials, environment, Also, just human error. Human error is probably the easiest one. You don't really need to get into depth. You can just say, oh, the guy timed it wrong, so it was off, or the angle was measured wrong, or the positioning was wrong. So you could literally say anything and it would count as a significant difference because you just say, he read the thing wrong. And that's like the easiest way to get the point, probably. But you cannot say human error, so actually don't say this. Specifically, do not use the words human error. You need to specify what human error. So an error during measurement, like overshotting, undershotting the measurement, pressing the timer button too early, too late. You need to say what exactly. Don't say human error, that's like vague. They don't like that. Part 2. For correctly, so briefly explain how the physical reason you identified in part C1 would lead to the decrease in the experimentally determined value of GEXP. So if we said they measured the angle wrong, since we know the formula was G equals A over sine theta, which we determined from last time, then we would just say, let's say we picked an angle wrong. So theta, sine of theta, so theta, if we say it went from like 0 to 90, right? The more theta would go up from 0 to 90, the more the sine function would go up. Well, yeah, because sine is vertical, so we draw the unit circle here. It would go up as we went up, because here it would be 1, here it would be 0 sine. So yeah. But it's in the denominator in this case, which means that the value where sine theta is smaller will be the value where g is bigger, and the value where sine theta is bigger will be the one where g is smaller. And here in our prompt it says that they calculated g to be significantly lower. This tells us that sine theta in the denominator was bigger, which means that they actually overestimated theta, or wrongly measured it to be higher, is probably a better way of saying it. So yeah, if you use theta, which we did, you could say that they measured the angle wrong in C1, and then you could say specifically how it leads to that using the formula here in C2. Alright, so here we have the last part of experimental design. We have two graphs that we need to fill out. In this example, we're going to start the card at the bottom. It's going to move up the ramp, and then when it stops moving at the top of the ramp, we're going to end our plotting the graph there. So we're defining the 0 position at the top of the ramp and the positive x direction at the bottom, which means that we're actually starting at a positive x point. So we're going to start our graph on here at positive x. And then as it moves up the ramp, it's going to go down in x value. So how are we going to plot this though? So we know that acceleration is pointing in this direction. Acceleration is going to be constantly pointing in that direction, which means that as the cart is moving up the ramp, we know that velocity is going to be decreasing at a linear rate because acceleration is constant. So we only work with constant acceleration in physics 1, and we know that when acceleration is constant, velocity will be changing at a linear rate. When velocity is changing at a linear rate, position will be changing at a non-linear rate because velocity is no longer constant, which means that position will have to curve concave up like this. It's not exactly a good concave up drawing, but something like that. Okay, I kind of messed that up. Draw it again. So like that. And then velocity, as we just said, would be linear because acceleration is constant, and in constant acceleration, velocity will be linear and the slope will give you acceleration. And here, the slope at any given point of the line tangent to the position graph will give you velocity, and that's how both of these are related. And that is the problem. Actually, there shouldn't be a part after 0 because it should stop at 0 because our bounds were defined as when it stops, momentarily comes to rest at the top before it starts going back down. You could have drawn the part where it goes back down on both of these, where position would have looked like this and velocity would have looked like this, with this being the negative part. But technically that's not what they asked for, but AP still would have given you full points if you did that. So that's experimental design done. Now we'll move on to the third question. Alright, this is question 3, the last one we'll be covering in this video. So we have a block mass MO attached to a spring constant KO, to a rod on a horizontal table. Rod has a motor. The system can spin at a constant speed at various speeds. When the rod isn't rotating, block is at rest and spring is unstretched. When the block starts rotating, the spring will stretch a certain amount, and that's the basis for all the problems. So let's look at part A. At time t equals t1, we have the figure on the left where the spring is stretching a distance d1 and the system is spinning a certain velocity. Figure 2 is the exact same thing, except the figure is probably spinning at a different velocity, and the distance that the spring is stretched is bigger now, d2, and it's specifically noted that d2 is greater than d1. So now let's go to the question part of part A. So we're drawing the force vectors for the spring force on both figure 1 and 2. So what do we know about spring force? We know that spring force is equal to kx. This means that it's directly proportional to the distance stretched. This means that force 2 has to be greater than force 1. Now that we know which one is bigger, we just need to determine direction. So if we go here back to the first page with the diagram, we can see that the spring is stretching in this direction. This means that the restoring force will act in this direction. Same thing for this one. The spring is stretched out this way, restoring force will act this way. So the direction for both is the same, except the magnitude for 2 is bigger, and our arrows should reflect that. So we can draw one like this and one like this, and that's 1. Now number 2, describe reasoning for drawing the arrows the length that you did, and that's exactly what we just did. So f equals kx. This is bigger in fig 2, which means that it's right. So that's part 2 done. Number 3, tangential speed at v1, is it bigger in the figure 1 at t1 or bigger in figure 2 at v2 t2? So the way that we can justify this is we know that the force pointing to the center can be described as centripetal force, Fc, and we know that that force is also a net force, and it has to equal the restoring spring force, which is equal to Fs. So both of these are also equal to mv squared over r, where v is tangential velocity, is equal to kx. X is the distance stretched, r is the radius from the center, and m is mass. So if we move things around, we get v equals square root of kxr over m. So all we care about here is x, because that's what's different in both. The x value is, which is the stretched distance, is bigger in figure 2 than figure 1, which means that figure 2 will also have a greater tangential velocity, which means that figure 1 has less. So we would check the box v1 is less than v2, except now I just read the part at the bottom where it says justify your answer without using equations. So same concept, you would just have to say this more qualitatively. So let me erase this and I'll do that. Okay, so without using equations, essentially we know that net force equals spring force, no other force is acting on the system. And then what else we can say is that as spring force increases, that means that the net force would increase. And as net force increases, we can say that tangential speed will also increase by extension. And that is all you have to say for this one. I think the numerical explanation is better, but you can't even use that, so whatever. Next part. Consider the scenario where a block travels in a circular path where spring is stretched a distance d from unstretched distance L. So here we're determining expression for the magnitude of the net force exerted on the block. Express answers in terms of these values that they give you. Okay, so first of all, it's net force, and as we just established in the previous problem, net force has to equal spring force, and spring force always equals kx. However, we cannot just say kx here. That would not get you the point, because we're given specific values to pick from. So we know that x is going to be the stretched distance, so substitute x with d, and then we're given a spring constant, it's just k naught, so k naught d, and that's the final answer. Easy. Okay. Part 2, tangential speed v. This is probably the hardest part of the entire thing, but it's still pretty simple. So that formula we derived for the one where they said we can't use formulas is exactly what we would use here. So centripetal force, which is a type of net force, will equal force of spring. So we would have k0d equals mac. So if we do that here, we'd get mv squared over r equals K0D. So let's solve for V here. We get V is equal to square root of K0dr over M. And in this case, it'll be M naught because that's the initial mass given to us. However, you'll notice that we cannot use R in our list because that's not one of the variables. So what will we use? So we know that the spring, I'll draw the spring up here briefly. So this is our spring. Let's say that this is the stretched length, this is the equilibrium. So radius will be total distance in the center, which means that we're going to add our equilibrium length plus the extra it's stretched, and that'll give us our radius. And you'll notice that we can use both L and D. So radius will just equal the sum of L and D. So we can substitute that. We would get V equals, okay, pen just glitched out. Eraser. Okay, so we'll just substitute R for L plus D, and we should get V equals square root of K naught D L plus D over M naught. You could simplify some stuff from here, but it really doesn't matter, so I don't recommend it. So after I draw that square root back in, then we're going to do part C. So does your equation for the tangential speed v of the block from part B2 agree with your reasoning from part A? So we're going to check yes because we did it right, and then here, let's look at this. V is directly proportional to D, which is exactly what we said in A. Remember, D is the extra distance we stretched it, and as this extra distance stretched increases, V will also increase because this is in the denominator. So with that reasoning, we know that it has to be right because that is exactly the same thing that we said in part 1, which is why we check yes. So our formula does match it, and we know the formula is right, so everything is right. Alright guys, thank you for watching. Be sure to like and subscribe and be on the lookout for our next video on AP Physics 1. Thank you.